It's worth noting here that function notation gives us a more compact way to express what we've expressed over here. Basically, in function notation, we can simply write all this out here. Now, we start with the assumption that y, which we now express as a function f of x, is ax to the p. I assume that you're familiar with function notation. You might not be familiar with all its advantages, and you might wonder why we even use it. But in any case, if y equals f of x equals ax to the p, then it follows that f of x2 divided by f of x1 is what? Well, f of x2 is ax2 to the p, f of x1 is ax1 to the p, and if you divide ax2 to the p by ax1 to the p, you get x2 over x1 to the p. In other words, f of x2 over f of x1 is just the same expression we got here when we did y2 over y1. But here we had to specify that y2 was ax2 to the p and y1 was ax1 to the p. Here we didn't have to write that out. All we had to do was say, okay, f of x2 over f of x1 equals this. And if we did the intermediate steps, they would just look like this. We wouldn't have had to say if y2 equals a, etc. We wouldn't have needed this line, so it's more compact. And then it follows then that the y factor, which is f of x2 over f of x1, is equal to the x factor raised to the p power, because x2 over x1 is the x factor. Now we could then say, okay, if x2 over x1 equals 2, then the x factor would be 2 and the y factor would be 2 to the p, and we would conclude the same thing we have here. Now, we didn't need to do this. This is more general than this. Here we're just going to assume that we have a value of x, and we double it, and we look at what the y factor is. And of course, this would be the y for the 2x, and this would be the y corresponding to the value x. So the y for the value 2x, y for the value x, the ratio of those two is what? Well, f of 2x is a times the quantity 2x raised to the p. If we replace x here with 2x, as we've done, then this x has to be replaced by 2x, and we get this expression. And then f of x, of course, is just ax to the p, which means that here's our ratio of y values. Now, we simplify this, a divided by a, so we could write that as a divided by a. I don't like cancellation. I'm not going to cross these out, because that would be, people will do things like they'll cross this x and this x out, and then they'll just get f of 2 over f of 1, and f of blank over f of blank. And that generally doesn't work well. It doesn't give us the result we want, although in this case it might. Okay, so we write down what f of 2x means, what f of x means, we simplify it. A over a is 1, so 1 times anything is that anything, so we don't have to write down the 1 here. 2x, it means 2 to the p multiplied by x to the p, and of course here we have x to the p, so out of the 2x to the p and the x to the p, we get 2 to the p and x over x to the p. So x over x is 1, 1 to any power is 1. We're just left with 2 to the p. The algebra is simple. The use of function notation is more elegant than what we did over here. It's more compact and it carries more meaning. But it takes a little more sophistication to use it and understand it. But the function notation gives us the same result we got over here, which is that doubling x changes y by factor 2 to the p. Again, on the premise that the function is a power function of the form ax to the p. Now let's just talk a little bit more about these graphs. If y doubles when x doubles, you're going to get a straight line graph. Okay. If y less than doubles when x doubles, your graph is going to have this characteristic. If y more than doubles when x doubles, you're going to have a graph with this characteristic, concave down here, concave up here. If y decreases when x doubles, then you're going to have a graph that looks very much like this. Okay? Now, you can characterize that. Let's just think about what we mean by powers of 2. Okay, now I think you can see everything on the board. But let me move the camera back just a little bit to make sure you can see the top. Okay, so first of all, we know that 2 to the 1 equals 2. And I'm just going to do some simple numerical reasoning here. 2 to the 1 is 2. So if p is bigger than 1, then 2 to the p is going to be bigger than 2. Because when p gets bigger, 2 to the p gets bigger. Now, there are algebraic connections we can make to that, but that's something you should understand intuitively. And if you don't, accept it for now, but think about it. 2 to the p, if p gets bigger, 2 to the p gets bigger. So that if p is bigger than 1, 2 to the p has to be bigger than 2. And if p is less than 1, it follows that 2 to the p has to be less than 2. You should really try to understand that. Okay, now, since if 1 is less than 2 to the p, which is less than 2, now remember the 2 to the p is the factor by which we change y as x doubles. So if the factor is between 1 and 2, you're going to have this characteristic. Okay, and that means the 2 to the p has to be between 1 and 2. And what? What power of 2 equals 1? Well, any number to the 0 power is 1. So 2 to the 1 is 0. 2 to the 0 is 0. 2 to the 0 is 1. Okay? So if p equals 0, then 2 to the p is 1, so that p would be 0. If p is 1, then 2 to the p is 2, so that p would be 1. Okay? So that 1 less than 2 to the p less than 2 means 0 less than p less than 1. That should be pretty obvious if you have some sense of how these quantities vary. And I'm not sure that you do because of overuse of the calculator. So hopefully you do. If not, you really ought to think about it. Okay, if p is bigger than 1, then since 2 to the 1 equals 2, 2 to the p has to be bigger than 2. And if p is less than 0, well, if p is less than 0, then, 2 to a negative power is 1 over 2 to that power. So 2 to the negative 3 would be 1 over 2 squared. It's a law of exponents that nobody seems to know. And we could write that as 2 to the p. If p is less than 0, 2 to the p equals 1 over 2 to the absolute value of p. So that 2 to the negative 2 is 1 over 2 squared, or 2 to the negative 3 is 1 over 2 cubed. If p is negative 3, the absolute value of p is 3, so that's exactly what this would say. If p is negative 3, then you'd have 2 to the negative 3 is 1 over 2 to the third. Now, we know that 2 to the absolute value of p is greater than 1, because 2 to the 0 is 1, and the absolute value of any number that's less than 0 is greater than 0. So 2 to the magnitude of p, 2 to the absolute value of p has to be greater than 1. Follows that 1 over 2 to the absolute value of p is less than 1. And since 1 over 2 to the absolute value of p is equal to 2 to the p, in this case where p is less than 0, it follows that this number is less than 1. Now, that's a fairly complicated argument, which you really ought to understand, but probably are going to have a little trouble understanding. Also, we can say that 2 to the p has to be greater than 0. That there's no number big enough that its reciprocal is less than 0. Okay? So, we can then classify these three graphs by the values of p. If p is between 0 and 1, we get this. If p is greater than 1, we get this. If p is between 0 and 1, we get this. And if p is less than 0, well, we can't generally define we generally, well, if p is less than 0, this is what we get. There's no power that makes 2 to the p less than 0. So this is the last possible case. So these cases, except for the p equals 1 case, which gives you the straight line, cover all possible cases of graphs of power functions. It's either going to look like this, or like this. Maybe more curvature, maybe more curvature, maybe more curvature here, or less curvature, but basically like one of these three graphs. Once more, to reinforce it, every one of these graphs has the rule that when x doubles, y changes by a certain constant factor.